Yes. Am I audible?
Yes.
One second, sir. Very good morning to one and all, and our special speaker for today's session number 1, Dr. Hemant B. Kaushik from IIT Guwahati. Sir, welcome to the board, and we are very happy to have such an eminent personality along with such a vast experience and knowledge to have something to take home for us. So we are looking forward for your session eagerly. Thank you very much, sir. Now I will hand over to Rishit for your esteemed introduction. Rishit, please.
Hello, may I audible?
Yes.
Hello, namaste. Speaker. A very agreeable morning to one and all present here. I, Rishit Chaudhary, on behalf of the Applied Mechanics Department, LD College of Engineering, Ahmedabad, and Government Engineering College, Modasa, welcome you all for the first session of 4th day of this 5-day short-term training program on disaster management and resilience building, conducted under the aegis of Directorate of Technical Education in collaboration with Gujarat Institute of Disaster Management, Gandhinagar. I hope you all enjoyed yesterday's sessions. To add to that joy, I would like to introduce the great personality we have for this session, Dr. Hemant B. Kaushik, sir. Sir is presently Professor in the Department of Civil Engineering and Center for Disaster Management and Research, CDMR, and also Associate Dean in Academics Affairs, Associated Faculty at the Indian Institute of Technology, Guwahati, Head of the Center for Educational Technology at the Indian Institute of Technology, Guwahati. Sir holds a bachelor's in civil engineering and a master's in structural engineering from Visvesvaraya Regional College of Engineering, Nagpur. Sir holds a PhD degree in civil engineering from IIT Kanpur, India. Sir has published more than 120 technical reports and articles in the journals, conferences, and workshops. Sir has received the Indian National Academy of Engineering INAE Young Engineer Award at 2010. Sir has also received the Best Paper Award in the conference organized by the National Institute of Technology, Rourkela, India on 2013. The paper, Finite Element Modeling of Confined Masonry Wall under In-Plane Cyclic Load, has received Best Paper Award in the theme Concrete and Masonry Structure. The paper, Historic Earthquake Resilient Structures in Nepal and Other Himalayan Regions and Their Seismic Restoration 2019, recipient the David Fischetti Award. The award recognizes an outstanding article in peer-reviewed publication that advances the field of conservation engineering. To list one of the awards, Sir has completed numbers of sponsored research projects, consultancy projects in his career. In addition to that, Sir was Principal Coordinator at Quality Improvement Program AICTE from 2019 to 2021. Sir was also Chairman in JEE Joint Entrance Examination Advance at 2017. Sir held many key positions at IIT Guwahati, NPTEL, GIAN, QIP are among us the few recent. Now, I would like to request Dr. Hemant sir to share his wonderful experience and words of wisdom with us on the concept of evaluation and enhancement of seismic capacity of unreinforced masonry buildings. Over to you, sir.
Thank you, Rishit. And thank you, Ms. Deepa, for the introduction and for inviting me to deliver a lecture in this very interesting short-term training program. I hope I'm audible.
Yes, sir.
Okay. So let me share this presentation.
Yes, sure. Right. Yes, sir. It's visible.
Yeah.
Yes, sir. Yes, great.
So I once again thank you for inviting me to deliver a lecture in this 1 week interdisciplinary short-term training program on disaster management and resilience building. I also welcome all the participants to attend this lecture. And my request is to not treat this next 1 hour, 1.5 hours as a lecture, but let us have an interaction. So whenever you have a doubt, please feel free to ask or write down your questions and I'll try to address them. We can also discuss in the end, but you can stop me in between if you want to ask any question. So today what we are going to discuss is some of the techniques using which we can enhance the seismic capacity or the strength or the lateral load behavior of unreinforced masonry buildings. So what you see here is this very interesting photograph where this person standing at the top is actually trying to stop or prevent the complete out of plane collapse of this building. This is unreinforced masonry building, as it is clear from the photo here. And what he has done is not really engineering, but somehow using these straps, which are actually some kind of textile or clothes, some bed sheets he has joined together and tried to prevent this complete out of plane collapse of this wall. Now our job is not to copy this, because there is no engineering here and there is no guarantee that this person will be able to prevent the collapse. But our job is to learn engineered methods using which we can prevent this thing from happening. And this is what we are going to discuss today. So I'll just summarize some of the existing techniques that are given in the code that have been used in the past by different people in different parts of the world. And also I'll discuss in more detail about a very simple strengthening scheme for these URM buildings, which is not only simple, but also very cost effective. In India, generally, there are large number of types of these buildings, but we can actually divide the Indian URM buildings into 4 or 5 different types. So I've just placed here 4 popular type of these buildings. So the most popular nowadays are the unreinforced masonry, brick masonry buildings with RC slabs. But if you go to rural areas, then these URM buildings with pitch clay tile roof, they are also common. And then the URM buildings with mud mortar and timber roof, and URM building with GI sheets. So these are also common, but we will not discuss the behavior of the last 3. We'll in fact discuss the behavior of the first one, because these are the simplest buildings to analyze. But compared to normal reinforced concrete frame structures, these are more complex. But among these 4, the top one is the simplest one. Now, if you look at the seismic vulnerability assessment studies that have been carried out in the past, all these types of buildings have been identified to be having medium to high seismic vulnerability by different researchers in different parts of the world. So all of these are seismically vulnerable. Some have more vulnerability, some have less vulnerability. These are some of the photographs that show the failure or the collapses of these buildings in the past. This is from the Bhuj earthquake. So you all have already seen these photographs. What happened to the railway, the railroad station, or to large number of buildings in Bachau village, and also to multi-story buildings which collapsed or failed or damaged significantly because of absence of some mandatory items or the members that is described by our design codes. Outside Gujarat also we have seen large number of such collapses. For example, in the North Kashmir earthquake of 2005, huge number of buildings in Uri collapsed. And you can see these are all government quarters, and the out of plane collapses, which are very common is in URM buildings, were very commonly observed during this earthquake. Also the in-plane damages, the usual cracks that are seen near the window and the door openings near those corners. This is a typical failure modes that is observed in case of URM buildings, plus the separation of the two perpendicular walls in the building. So all different types of damages were observed. We generally observe after the earthquake, most common building failure is observed in case of URM building, followed by some other types of buildings. Now, interestingly, some of the buildings which are primarily unreinforced masonry, but in which some additional members in the form of these timber logs were inserted at different locations. So here you can observe different timber logs in different directions in the building. So these buildings, they survived the earthquake without much damage. So this is, for example, is the photograph of the Diwari system, where timber laced masonry is laced with timber. So basically what we do is we confine the masonry wall such that instead of having a large panel, we divide that into very small panels, thereby increasing its resistance in both in-plane as well as out-of-plane loading. Similarly, other types of buildings in which we insert some elements. These are not reinforcing elements, but somehow they confine the masonry wall to improve their earthquake resistance. So this is a TARC system, where again you can see that the timber logs, these timber logs, they are actually embedded in the wall. So what happens when these people, they find that there is a damage to a certain portion of the wall, or they expect some damage there, they insert some timber logs, they reduce the free length of the walls or the slenderness ratio, because they understand if the wall is too long or if the wall is too high, it's vulnerable to collapse. So this is what they have done. And interestingly, these buildings survived that earthquake, 2005 earthquake, without much damage. Then we move on to another small earthquake in Sikkim. This is the 2006 earthquake, very small earthquake, but still there was significant damage in Gangtok city. Now there we observed a very old unreinforced masonry building. This is it. This is the archive building. It used to be the assembly building before 1988 Bihar-Nepal earthquake. But after that earthquake, some damage occurred in this building and the assembly was shifted to a new building. But this building was retrofitted using these steel bands. And you can see these steel bands, they run from top to bottom, vertically as well as horizontally. So these steel bands are provided around the openings, window and door openings, as well as they are provided along the whole length of the building at sill level and at the lintel level. So these steel flats, their dimension is very small, and they are provided on both the sides of the wall. They are then connected with the help of nut and bolts, bolts and nuts, by drilling the hole throughout this wall and then connecting the steel flats on both the faces of the wall. It's a very simple arrangement. So after this 2006 earthquake, the building did not suffer any appreciable damage. It suffered damage in 1988, but retrofitted building did not suffer much damage in 2006. In 2011, another earthquake of very high magnitude, 6.98 occurred. And those who have done earthquake engineering course, they can understand that this difference in magnitude of 5.3 to 6.9 is huge. Right? So because of this earthquake, this building also suffered some damage, but then it did not collapse. Even none of the walls suffered severe out of plane damages. So here you can see what happened to this steel flat here. It has bent, but then it has actually prevented the out of plane collapse of this wall. You can imagine what would have happened if this band were not there. Right? So this clearly shows that these bands actually are very effective in preventing the complete failure or the collapse of these structures. At some locations, we could observe that these flats, they have broken at the corners. So which clearly show that they are resisting the load. There were some problems related to the rust, related to the poor maintenance, but that can be taken care of because these bands can be replaced very easily. Now, similarly, there are other solutions that have been proposed in the code, not only in India, but in other countries. For example, this Iran earthquake, we observed that those buildings in which the minimum code requirements were satisfied, they survived the earthquake without much damage. Now, what are these minimum code requirements? We'll discuss in detail. But then there are some structures which are very old. Even in the developed countries like New Zealand, we observed huge damages to these URM buildings in 2011 Christchurch earthquake. So these are mostly the churches which collapsed after this earthquake. Large number of churches collapsed. So it's not only the underdeveloped or the developing countries where URM buildings suffer damage. Those buildings in which some strengthening schemes were provided, like this, here you can see this X type of bracing is provided. So these buildings survived the earthquake. This is again a URM building, but then the owners, they retrofitted it using this X braces. And here also you can see that the building suffered repairable damages. This is again retrofitted using the externally provided these steel members. So then some of the common observations are the area of the walls or the portion of the walls near the openings are most vulnerable, and that we already understand because near the corners of these openings there is a huge concentration of stresses which actually result in initiation of damage, and this damage is then propagated to the other parts of the wall. Out of plane collapse of the walls, it is a most common type of failure observed when there is no proper connectivity between the walls, different walls, perpendicular walls, and the poor connectivity between walls and the slabs. Also, if there is a poor connectivity between other structural elements. So because of this poor connectivity, out of plane collapse generally occurs. The traditional masonry buildings laced with timber logs, they survived. Now, another interesting feature here is these traditional buildings have very thick walls. These are not like normal URM buildings. So that also the high thickness of these walls, large thickness of these walls, they also help in preventing the collapses. So such buildings performed nicely with repairable damage. The shear failure observed in walls with larger and more number of openings. So we all understand that in case of URM buildings, openings are not good. And moreover, the location of opening also plays a major role in deciding how much will be the strength of the building. Then some buildings which were constructed by following the design codes, for example, by providing the lintel bands, sill bands, and those buildings in which some strengthening schemes were provided, they also displayed satisfactory performance with some minor damages. Now the question that comes to our mind is why we are not strengthening these buildings. The answer is simple, because it is not easy to strengthen a URM building, and we don't have proper design and construction guidelines for such strengthening schemes. There are a large number of strengthening schemes discussed in literature, in research papers, in books, but unless the scheme is inexpensive, unless the materials required, the raw materials, the labor, unless they are all available locally, it is very difficult to use these strengthening schemes in large scale. I mean, if you know the number of URM buildings in India, they constitute more than 85 to 90% buildings in India. So still today we have, among all the buildings constructed in India, we have about 85% of them as URM. And don't be misguided by looking at Ahmedabad or such big cities, Surat, where you get reinforced concrete frame buildings. But if you go to slightly outside these big metropolitan areas, you will find more and more number of rural buildings, URM buildings. So unless we have a design guideline, construction guideline, and inexpensive strengthening schemes, we will not be able to strengthen these buildings in large scale. Now let us look at the earthquake scenario. The major problem here is why we are lagging behind. If you look at the seismic zoning map of India, we all know that there are 4 seismic zones in India. Zone 5 corresponds to the highest seismic zone and zone 2 corresponds to the lowest seismic zone. There's no zone 1. Every part of India is having certain seismicity today. Now on this seismic zone map, I have superimposed some circles or the ellipses with different colors. The population density is also shown here, and the URM building density is also shown here with the help of these circles. So if you look at the color of this circle, it indicates the population, right? So red color circle means it has more than 1000 million population. Blue circle means it has population ranging from 50 to 1000 millions. And then yellow and green. So this color represent the population, and the size indicates size of this circle. It indicates the density of the URM building. So the number of URM buildings. So smaller the circle means the URM buildings are also smaller in number. Bigger circle or ellipse means the URM building is also higher in number. So now you are here, you can see this region, highest seismic zone, and you have significant number of URM buildings. Again, this region, Bihar, UP, this region from Ahmedabad, Maharashtra, and then south. So you can see here that the population density and the URM buildings in some parts of country, they match, and which gives rise to very high seismic risk in some of these areas. So huge stock of URM in populous regions with high seismicity. So a combination of these 3 factors, it gives very high seismic risk. Okay, so with this background, let us study some of the structural failure modes of masonry walls, how they fail. And if we understand the failure modes, we can then decide how will these walls or buildings be retrofitted. So there are primarily 2 types of failure modes. One is in-plane failure mechanism and the other is out-of-plane failure mechanism. I hope you understand what is meaning by in-plane. In-plane means this wall will resist the load in this direction only along the length of the wall, and the failure will also occur along its own length. So here is the flexural failure, which is so obvious that we are applying this load horizontally, so we get these flexural cracks and in the form of maybe bed joint cracks or sometimes along the head joints also. Then we have the sliding failure. So when we have lower vertical load, the vertical gravity load on the wall is less, then the whole wall can slide along the bed joint. Then we can have a rocking failure, a combination in the cyclic loads when we have to and fro loading from left to right and right to left. So such kind of rocking failure where the wall dances around about any bed joint is very common. So we'll have failure at both the ends here. And then the diagonal shear mode of failure is also commonly observed, where we have such kind of cracks which propagate through the joints. In the out of plane failure mode, as we discussed, if we have poor connections between these two walls, perpendicular walls, also if we have poor connection between the wall and the slab above, then it is obviously this wall will actually, under the action of this load, will fail in the out of plane direction. So when the direction of earthquake shaking is like this, these two walls, they will resist this load along their own length. So these walls A, they resist in the in plane direction, but walls B will resist this load in the out of plane direction. So they may topple because of poor connection between these perpendicular walls, and this is what is shown in this photograph here. Then we also have the story shear mechanism, where because of the variation in the wall thickness, because of presence of the poor quality of masonry, or because of presence of large number of openings in thin walls, the whole story may collapse. For example, here you can see the whole story. It has because I mean, if you look here, this part did not collapse, or even this part, there were large openings, right? So that gives rise to such kind of story shear mechanism. You can see here that the pier of the masonry wall between these two openings was so small. Then when the cracks started developing, this part simply collapsed. And then wall overturning, you've already seen that not only single individual walls, but the entire length along the whole length of the building and some part of the wall in the perpendicular direction, they can overturn. This is what happened in this building. Again, the reasons are similar because of poor connections, because of smaller vertical load. These may happen. If we install or if we construct some ring beams or the lintel beam or the slab beams, I mean the bands at different locations, then we can prevent such kind of failure, because that band will actually help in creating a box action in this building. So this is another failure mode. And then the vertical instability sometimes occur because of the poor quality of masonry, because of presence of some intermediate floors and poor embedment to the wall. So sometimes we can have vertical instability like it is shown in this photograph. Okay, so primarily because of the poor material use. So you can see here different types of materials used. These are brick masonry, but here we have stone masonry, some part, and the building is not regular. Therefore, you have such kind of instability. Now, before discussing the one simple solution to retrofit these buildings, let's quickly discuss what is there in our design codes. So we have some codes in which some recommendations have been given. For example, this IS 4326 1993, it has given some recommendations for openings, for using the mortar mixes, recommended mortar mixes for different category of construction. And you can see here, these are the door, ventilator, window and cross walls denoted by 1, 2, 3, 4. And it gives you different dimensions, like what should be the height, what should be the distance of this door from the edge of the wall, what should be the distance between two openings. So a lot of dimensions they have given here, in addition to the recommended mortar mixes. Okay, so these are some thumb rules using which you can actually decide where to place the openings and what type of mortar mix I should use. So these are the dimensioning. So you can see for different categories of buildings, what will be A, B, C, D, all the dimensions are given here. But these are all thumb rules. Then the earthquake resistant design and construction of buildings, the code of practice. This is the title of this code. It also tells us about the provision of the lintel bands, roof and floor bands, and vertical bars at specific location. So the code recommends that you provide a lintel band above all the openings, and this lintel band should continue along the whole length of the building, which we already know. Then it also tells us that if possible, we provide some reinforcement at the corners of the walls. The reason is simple, that we need to improve the connection between these perpendicular walls, and that we do by inserting a reinforcement at the corners. Okay, so some dimensions and some thumb rules for the diameter of the bar, the spacing of the bar, they are also given in the IS 4326. Then we have another code for improving providing alternating tooth joints in walls at corners and T-junctions. You can see here that at all junctions of the walls, it is recommending that you provide such kind of tooth joints, which are generally provided in confined masonry buildings, also at the corners. And some thumb rules are given on what should be the length and where should be provided. The code also recommends to strengthen the masonry around the opening. Okay, so by providing such lintel band and by providing the toothing, by providing vertical bar around the opening. So this is all given in the code without design equations, without distinguishing between the size of the openings, the location of the openings. Just some thumb rules are given so that you can develop upon these rules to decide how much and where to provide these schemes. And then some repair methodologies are also given in the code. For example, here the grout or the epoxy injections can be provided, can be inserted in the existing weak walls. Then the IS 13935, which is for repair and seismic strengthening of buildings. It has some strengthening schemes for these URM buildings by pre-stressing. So these are the pre-stressing rods, right, and the anchor plates. So it says that it recommends that you can pre-stress these individual walls in different directions. But you understand it is not easy to pre-stress the URM building. Then the splint and bandage strengthening technique has been discussed in the code. It says that you can have this wire mesh with width greater than or equal to 400 mm. And you put this wire mesh above the wall, and then you plaster it, or you plaster it. So some of these techniques are given, but it lacks the detailed information about how to design these strengthening schemes. So for that, we need the tensile strength of masonry. And in our code, there is no mention of the tensile strength in these codes. There is some mention of tensile strength in IS 1905 for different categories of loading. No information on a particular type of strengthening scheme for a particular requirement. So just thumb rules with some pictures are given. Then application of some of the proposed methods, they require spatial materials and skilled labors. For example, it should not be expected that the URM buildings, normal URM buildings, not the special very old assembly buildings or such kind of buildings, but normal URM buildings in which people live, anybody will pre-stress those buildings. It is highly expensive. It requires special materials, skilled labors. It's not practical. Then few methods are quite simple to use, and they are also inexpensive, but there is no detailed design guidelines. So it's difficult to use them also. So these codes, existing codes, the only broad guidelines are given without specific reference to the required capacity or the demand. So this is what we'll try to do for one particular scheme. We'll try to develop specific guidelines for capacity as well as demand. This slide shows what is the international status. So many techniques have been used internationally, from ferrocement to shotcrete, grout injection, then provision of external reinforcement, then confining the masonry, post-tensioning the masonry and providing a central core for increasing the strength and stiffness. So large number of schemes have been studied experimentally. But what we are going to do in this presentation, we will discuss the use of the steel elements in the strengthening of URM buildings. Now, if you look at some other earthquakes, for example, this building is a mosque which was damaged after 2004 Sumatra earthquake and tsunami. It was slightly damaged. You can see some of these minarets, they collapsed. Earthquake, but otherwise nothing happened to this URM building. There is a reason why nothing happened. You can see these elements here. These are steel bands, steel elements which were actually used here. Also you can see. So these steel elements were used to retrofit these buildings long back. There was an earthquake in 1942. After that, these buildings were retrofitted, and the maintenance was so good that nothing happened to these buildings. Similarly, the steel elements here prevented the collapse. These are the steel elements that prevented, but of course these are expensive. But what we are interested in studying this scheme, which is very effective and which appears to be very inexpensive also. So what we have done in laboratory, we have tested 3 walls first. So these are full scale walls, 3 meter height by 3 meter length. And we tested 3 walls, one without opening and the other with door and the window opening. So loads were applied laterally at the top of the wall. So this is a reinforced concrete slab at which the cyclic loads were applied in this fashion. The history is given. These are some of the properties of the materials. So you can see the brick unit strength was 19 MPa and the masonry prism strength was 3.18 MPa. So other properties are given here. And this is how these 3 walls, they failed. So you can see the entire sliding, the entire bed joint sliding occurred here in this wall. Although we applied some axial load, considering it to be a 2-story wall. Some crack here also. So this was one type of failure that we have already discussed, right? Then in case of openings, we found here the crack emerging from the opening, the door opening, plus also the vertical, the horizontal cracking at the bottom. And in case of opening, window opening, we did not find any crack here, but again, there was a sliding at the bottom. This was because of the lesser load at the top. So it clearly shows one beneficial influence of this lintel band. Though it was not provided along the whole length, but remember it is not a building, it is single wall. So you'll not be able to understand the whole implication of not providing the lintel band, but in the building we will understand. So this study was just conducted to understand how individual walls behave during this lateral loading. I'll show you a video, and you can then see how this building behaved or performed when this lateral load was applied with the help of this servo-controlled hydraulic actuator. So the loading was applied at the top, and what you generally see in case of reinforced concrete frame testing, you will not see here. Let me first show you the video, then you'll understand what I'm saying. With the help of the or not. Cyclically at the top, and then suddenly we see the cracks and the failure. It is because this masonry is very poor in tension and it behaves like a brittle material. So it doesn't give any sign of any yielding or any high deformation. We cannot see much, right? It's with the door opening, which is WS2. Its performance was poorest. The strength was very low. Am I audible now?
Yes, sir. Yes, sir.
Yes, I mean some connection issue in between, I think. Let me again share.
Yeah.
I hope it is visible now.
Yes, sir. It is visible. Yes,
Okay.
sir.
So I hope you heard up to this point. The envelope curve. Okay. Fine. So after this wall testing, what we did, we tested the whole building. So here you can see that this is a full scale room constructed using this URM unreinforced masonry. So the size of the room was 3 meter length. It's 3 meter wide and 3 meter high. And we tested this single room without retrofitting. This is a slab constructed over the walls, and these are some loads which actually represent the load coming from the upper floor. The building was tested under the hydraulic actuator at the slab level, and we use large number of sensors to check how the building responds. Then we retrofitted this building using a single steel flat, which was applied at the lintel level only, along the whole length, as shown here. Along the whole length, we have applied along the periphery, we applied this steel band on the both faces of the walls, all the walls. Then we retrofitted the building using such kind of an arrangement where the steel flats were provided at the lintel level, at the sill level, and around the openings, around both sides of the openings. So this was also continuous along the periphery of the building and on both faces of the walls. The connection of these flats were done with the internal flats by drilling a hole and then by connecting using nut and bolts. You can see here the size of the steel flat that we used was 40 mm by 5 mm. So very small size. And this is how the testing was done. So you can see here the size of the building, the type of the connection between the actuator and the building, and then the LVDTs used to record the the displacements in plane as well as out of plane direction. The building was supported over the reinforced concrete slab. And which was connected to the rigid floor. So these are the some images in the plan. So you can see here, this is the flats were connected using this
Sir, I think there is some network issue.
I think there was another connection problem. Am I audible now?
I'm তোমার mic mute છે.
Yes. Sir, you're audible.
Yeah, so now I am not opening my camera just to prevent the bandwidth loss. So let me again share.
Yes.
So what I was saying that let us see the video of the lateral load response of this unreinforced masonry building without retrofitting. And then you can see how this building has behaved, how different cracks are formed in different parts of the building. So this is that video. Top part of the building was actually separated here. So this part of the building was completely separated from the bottom part, and it was moving as if it is a completely different building. Then we retrofitted the building using this single band at the lintel level, and we observed similar kind of damages around the openings and in different walls. We also observed that the failure of this band took place near one of the corners. And here is the at this level. And similar kind of failure was observed, though the amount of cracking was much less in this case. Finally, we retrofitted in the model 2, the second scheme, we retrofitted using these steel bands at various levels around the openings and at sill and lintel level. And let us see the video of this test. So again, though the damage started here, but they did not go like diagonally. In case of URM, we found these diagonal cracks, but now they followed this lintel band in the horizontal direction along the whole length. We used large number of strain gauges on the steel flats all around wherever we provided. We used these large number of strain gauges. So let us see how these strain gauges they recorded the strains. So I'm showing you the strains recorded in 63 number of strain gauges, and you can see how much is the strain. So in some of these strain gauges, the yielding was very properly recorded. So for example, this was of course this strain gauge, of course, failed. Not the strain gauge, but the steel flat it actually failed. But some of these other strain gauges, they recorded the yield displacement, which clearly show that the steel bands or the steel flats, they resisted the lateral load remarkably and very effectively. These are the hysteresis curves for the three types of three buildings that we tested. And obviously you can see this third type, the strengthened building, in which the multiple bands are provided at different levels. Its capacity was higher. Not only the strength, but also the deformation capacity was much higher compared to the other buildings. This is the comparison of the envelope curves, and this red curve is for the second strengthened scheme, and you can see an improvement of about 38% in the lateral strength, plus about 50% in the lateral deformation. Right? But when we consider this first scheme, in which only one flat was provided, there's not much improvement in the strength as well as deformation along both positive and negative direction. Also, the cumulative energy dissipation capacity of this model 2, the strengthening scheme 2, was much higher. It shows the effectiveness of this scheme. So like I said, an improvement of 38% is huge in case of URM building. And of course, the increase in the lateral deformability was about 50% more. And these strain gauge readings, we observed that the corners of the openings are the most critical areas that need special attention. And the application of steel flats can significantly improve the lateral load behavior because it increases the load by 38%, increases the deformation by 50%, and therefore they can reduce the seismic vulnerability of these buildings. One of the major advantages of this strengthening scheme is that we can very easily replace these bands or repair these flats whenever we need it. It's not a very big task. So after this, we carried out some numerical simulation because we wanted to carry out some further studies to develop some design equations so that people can very easily decide what is the section size required for the steel bands, where do we provide them. So for this, we carried out numerical simulation using different software, Strand 7 and Abacus, and you could see that we could simulate the real behavior using both these softwares. So there was some calibration done to achieve this calibration related to loads and materials, but we finally could simulate the realistic behavior. And here you can see the comparison between the experimental envelope curve and the envelope curve given by Abacus and Strand. So the Abacus and the experimental curve were more or less matching. Strand curve, it gave us very good results up to the strength value, but not beyond that. We use these results, these calibrated models, in doing finite element study by varying different parameters, by varying the thickness of the walls, by varying the I mean, here only the thickness and the width of the steel flats have been varied to understand the influence of using a very big steel flat, in the sense the size is big, compared to a very small thickness or very small length steel flats. So the influence of using different sizes of the steel flats. But it's very clear from this figure that the size of steel flat doesn't really matter, because most of these curves, they overlap each other. Right? So this is the URM curve, okay, and unstrengthened, and all other curves, they are overlapping. So whether you use a 5 centimeter 50 mm by 1 mm or 100 mm by 1 mm or 150 mm by 1 mm or 200 mm by 1 mm flat, it really doesn't matter. Even a small flat will give you similar kind of result. Similarly, in other case, we varied the thickness, keeping the width of the steel flat same. So 50 mm by 1, 50 mm by 2 mm, 50 mm by 3 mm, 50 mm by 4 mm. Again, there is not much variation. More or less, the results were similar. And here, what we did is for second scheme, where we provided these steel bands at different locations, we did the same study. Again, no difference. So this clearly shows that we don't really need a very big size, bigger size of the steel flats. Only the minimum size steel flats will be able to give you very good results. Increase in strength and deformability. Now, in addition, we also carried out some parametric study by varying the thickness of the wall and by varying the aspect ratio of the different the piers and the building, the walls. So based on that, we developed this design equation by carrying out regression analysis of all the parametric analysis. So what we developed finally is this equation, which gives you the ratio of the lateral load that the building can carry and the self-weight of the building. This is this alpha L, the ratio of the lateral load to the self-weight. And we can find it if we know Ft, which is the tensile strength of masonry. If we know Ar, which is the aspect ratio of the building. If we know T, which is the thickness of the wall in the building, and As, which is the cross-sectional area of the steel. So the parametric study involved variation in all these parameters. And finally, we developed this equation, which gives us, which predicts the strength value with less than 20% error. So which is remarkable, because in URM building, in masonry, the errors are much larger because of lack of material quality. There's this huge variation in the materials when we go to different places. So this 20% error is not much in case of masonry building. So this is a good equation using which anybody can actually design these strengthening scheme. So with this, let me thank the person, my student, who actually did all that work is Dr. Thangsumong Chaudhary. It was his PhD work. And I also thank the Department of Science and Technology for funding this study. With these two photographs, that shows how rich we are in our masonry construction. So both of these buildings are more than 100 years old. And this one is in Assam, and this one is in Tripura. And both these buildings have survived the test of time and earthquakes. Both of them are in seismic zone 5. And this Ujjayanta Palace has actually been retrofitted recently, but this building, the Karingar, has not been retrofitted. So thank you very much for patiently listening to me. And if you have any questions, we can discuss.
Yes, sir. Thank you very much. Let us proceed to interaction participants. I see. Dr. Ankit Patel, you may start with. I shall be enabling the mic. Yes.
Good afternoon, sir. Ankit here.
Yeah, good afternoon.
Sir, if I can share my slide.
I can't hear you.
Can you just give me the right to
Ankit,
share
sir,
slides?
please unmute yourself. Okay. Yes, Ankit sir, now you are presenter even.
Just
Ankit sir, am I audible to you?
yes, ma'am, you are audible. Yes, now I can share my screen. Just confirm. Is it visible?
Not yet. You need to share the screen.
Okay, just a minute, ma'am. Just a minute.
Yeah, I think we got you. Yes, you are there.
Thank you very much, ma'am, for giving me the rights. Sir, actually, this one is a site from Modasa, one of the site near to the engineering college, and this kind of. Can you just give some few comments regarding the basic reasons behind this kind of problems at the sites? Actually, they have three of the buildings. They have this kind of problem. So, just if you share some idea about it, it's very helpful to us.
Dr. Ankit.
Yes, sir. Yes, sir.
It is a very good opportunity to meet and discuss. Invite me.
Sure, sir. Definitely, we'll make some arrangement.
It is not possible to just have a look at this photograph and tell you exactly what is happening. Okay. Right? So, maybe if you can go to site and do a video call, let me see. Otherwise, it's very difficult to tell you from here.
Okay,
So
no problem.
Let us
No
meet.
Problem. Definitely, we will arrange. Sure. One reason that we have found, what happened at that site, after mixed design, after concreting, they have found that there is some problem in this sand. They have majority of content of sand is silt and clay content, I think. And due to shrinkage, this kind of error are there or not? These kind of problems are there or not?
Yeah, there can be because of shrinkage. It may happen because of many other reasons. It may happen. So if you have non-destructive testing facilities with your college, then try to see some of these things. What is the strength of concrete? Where are the placement of steel proper? So these are the things you can do.
Yes, sir. Okay, sir. Thank you very much, sir. No issues, sir. We'll meet. Definitely, we'll arrange some this kind of meeting also.
Sorry to disappoint you.
No problem, sir. Okay, sir. Thank you.
Okay.
Okay. And any other questions from participants? Welcome. Yeah, Palak, please go ahead. Palak ma'am, please unmute yourself. Sure. Go ahead.
Hello, sir. Myself,
Yes.
Palak Shukla from KJ Polytechnic, Bharuch. Sir, I just want to know that which type of instrumentation have you used for cyclic load application?
These cyclic loads were applied using displacement controlled actuators, which were made by MTS. So these are servo controlled actuators, and the response was recorded using LVDTs at different locations and the strain gauges over the steel flats. Primarily these were used.
Okay, sir. Thank you.
Yes, Mr. Ronak Matiani, please go ahead. Unmute and please go ahead. You're muted, sir. Okay, got you.
Hello. Good afternoon, sir.
Yeah.
Thank you for this wonderful session on the unreinforced masonry infill and its behavior. So I have one question about which is somewhat related to unreinforced masonry part. Sir, when we design a building or when we go with the construction of unreinforced masonry building, these are generally 2-story, 3-story, limited to that part. We generally do not see high-rise building and all this stuff. So, sir, in this unreinforced masonry building, do the soil conditions affect the performance of the building? And sir, if it affects the performance of the building, then why do we take a constant acceleration zone, that is factorial acceleration as 2.5, that is suggested by IS 1893 2016?
Yeah, of course. Any structure that has mass and stiffness, that will be affected by the ground conditions, by the soil conditions. Right? If you have these masonry buildings are known to have huge mass as well as huge stiffness. And moreover, they are brittle. Right? So they possess all the properties which we don't want actually in a proper building that is constructed in highly seismic zones. But still, they are very popular in almost every seismic zone because of easy availability of the materials. And we don't need very skilled laborers, right? It's not very expensive to construct unreinforced masonry. So this is the reason these buildings are very popular. So of course, the soil properties affect. And as far as your second question is concerned, why do we have that constant acceleration zone? This is to actually avoid people from deliberately reducing the design loads on these buildings. Because if you don't have the constant acceleration zone on in the design response spectrum from this 0.1 to 0.4 or 0.35, 0.55, depending on which soil type, if we have haphazard or random distribution of the acceleration, you appreciate that in some cases, because of variation of a because of small variation in natural period, you will get very different values of acceleration. And then the design loads also. Right? So just to avoid that, some minimum design loads, they are specified. And moreover, in the new code, you will also find that even if you use this design response spectrum, there is a table given which limits the lower value, that you cannot design below certain level. Yes. So these are all, yeah. So these are all to prevent misuse of the code. That's all.
Okay. Thank you, sir.
Other questions from participants? Okay. Meanwhile, others go. Sir, I would like to put one question. Has any effect of this steel flat bracing belts instead of that continuous belt, any effect of bracing pattern like somewhat zigzag has been explored?
No, it has not been explored anywhere. We can do that study, but there will be limitations because of presence of these openings, right? So we generally don't have external walls without openings. So we can't have the diagonal running steel flats across the whole length. We have to discontinue it. And when you discontinue the steel bands, its effectiveness reduces drastically. So the effectiveness is there because these steel bands, they run across the whole perimeter of the building. They improve the box action of the building. But we can, of course, try using these steel bands diagonally and in some other configuration. We need some funding. We need some good student. We can, of course, try.
Okay. Okay, thank you, sir. And then instead of it band being straight, can it be undulating like zigzag or little curved? Does it have any effect? Will it have any effect?
It may have effect, but you see, when we start doing all these zigzag things, we are also increasing the cost. So one of the primary goals of this study was to actually develop a scheme which can be used by a huge number of people. See, the cost of this scheme that we have studied is about 800 rupees per running meter. 800 to 1000 rupees per running meter. This is so inexpensive. But when you do this zigzag, when you start doing all those things, you will be requiring more and more amount of steel, more and more amount of labor. So the cost will increase first. Second, we are really not interested in increasing the lateral strength. We are interested in preventing the out of plane collapses, in preventing the in plane severe damage. This we have actually successfully done using the horizontal lintel bands, the sill band, and the bands around the openings. So this was successfully done. Now the only thing that we can do is to further improve the deformability or the ductility by maybe, as you suggested, using some diagonal elements somewhere. But again, it will increase the cost, and that will prevent the common people to use these schemes in scale.
Yes, sir. This must be the best, right? I agree, sir. Totally. Okay. Any more questions from audience participants? Panchal sir, please go ahead, sir.
Okay, first I would like to thank sir for giving the wonderful presentation. Am I audible, Deepaben?
Yes, sir, very much.
Okay.
Sir,
so my question is regarding the cement mortar bricks and the burnt clay bricks. So nowadays the use of cement mortar bricks been found increased. Okay. So my question is, sir, which brick is more preferable performance-wise, cement mortar brick or burnt clay brick, sir?
See, let me give you one example. The burnt clay bricks, if you are in Karnataka, the strength of burnt clay brick is only 2 MPa, 2.5 MPa, 3 MPa.
Okay, sir.
Okay. If you go to Uttar Pradesh, the strength of individual bricks, burnt clay bricks, it increases to about 30 MPa, 35 MPa. If you go to Imphal, the capital of Manipur, if you go to Imphal, the strength of individual bricks can be as high as 45 MPa, 50 MPa.
Yes.
So the material, of course, matters, but then simply by saying that burnt clay bricks are better or cement mortar bricks are better is not the thing that we as structural engineer should look into. We need particular strength. That strength, if we are getting from burnt clay bricks, it's good. If we are not getting, then we have to look for some other alternative, because the strength of bricks is of paramount importance as far as the URM buildings are concerned. Remember, these are not the infill walls. These are the load bearing walls.
Yes, sir.
So we need very good strength, very good quality of bricks. So whichever material is giving us that quality, we should go ahead with that. Now, having said that, there are other issues related to the use of this material. For example, the burnt clay bricks are very good if you try to drill holes into them. The burnt clay bricks are very good for water resistant, for thermal resistance, for sound resistance, sound insulation. But some other types of bricks, they are not good. Even you cannot drill holes into them, right? So they will simply fail. Similarly, the thermal insulation, the water absorption, the initial rate of absorption of different types of bricks that are coming up nowadays, they are not up to the mark. So the basic point point that we should remember is testing all the properties of these bricks before using.
Yes, got sir. Got it, sir.
Thank you.
Okay. Sir, one more question from Mr. Ronak Motiani. Sir, go ahead, please, Mr. Ronak.
Yes, thank you, ma'am. Sir, you discussed a very cost-effective technique for the retrofitting. Sir, is there any cost-effective technique for assessment of retrofitting? We have flat jack test and all that part for masonry, but generally, when we see any report of masonry building that is being tested, they generally go with rebound hammer test on the slab and then they give the results. We have flat jack test and many other tests that is obviously there. But if having such a cost-effective retrofitting technique, do we have any simple or a cost-effective technique that can assess the strength or any other part of that, sir? Whether we should go with retrofitting or not, sir?
Unfortunately, no. The assessment is never easy. The retrofitting, post-construction retrofitting is never easy. It is not cost-effective in most of the cases. Of course, you need to do that NDT, the flat jack tests, and if possible, we sometimes go ahead with by collecting some material. If some bricks are available or even the mortar, if available, we can bring and do some microscopic study to understand the proportions, the type of constituents in that. And if some bricks are available, then that is the icing on the cake. We can actually see what is the actual strength of those bricks. So this is what we do.
Okay, sir. Hello. Okay, sir. Thank you.
Any further questions from participants? Okay. Sir, may I go for one more question, if you allow us?
Yeah, please go ahead.
Sir, apart from cost, is it a possible reason, does it have a valid reason to explore for composite material bands kind of thing?
Yes, why not? We are actually doing that. See, when I say cost, that is for 85% of the people, right? But 15% of our country, 15% of people in our country are rich. They can afford other retrofitting schemes. So why not? So we are studying several other retrofitting schemes, which may be used in other types of constructions, and those who can afford, they can use it.
Okay, thank you, sir. Thank you. Then we will surely think of researching in this area also. Then any more questions from participants? I guess no. So now I would like to thank Professor Hemant Kaushik sir for such a wonderful presentation. Now we got to know, I think everyone must understood that why you have received so many awards for paper presentation as well as conference presentation, sir. It was so thorough and very well intricated. Like this was our first session considering earthquake as one of the disaster. Even though the whole content was very easy for us to understand, because the journey has been a real good, I would say. You have so nicely explained to start with introduction, behavior, then possible vulnerabilities, and then solutions. Like we are feel like we are updated totally on this area from research point of view. We can, many of our students will be willing or starting thinking to jump into this area for their ME project and so. So it has been a real good a new area you have opened up for us. In even recent years, this last year we had two training on earthquake resistant structure as well as confined. from Svetlana Madam. And with your lecture pairing up it with, we will be highly motivated to continue further work. Many of our departmental faculties are carrying out research in this area, and it will surely benefit them a lot. Thank you once again, sir. It has been a real nice experience. I think our participants will totally agree to it. We will see feedback, but it has been a wonderful lecture. Thank you so much, sir.
Thank you. Thank you all for inviting me. And thanks to the audience for patient listening.
Yes, thank you very much.
So can I leave now?
Yes, sir. Sure, sir. Sir, if possible, will you please provide some of the PPT on research and this for audience participants' reference?
Yeah, I will send you the handouts. I will send you the handouts.
Okay.
Yeah.
Okay, sir. Okay. Thank you.
Okay.
Thank you. Thank
Bye
you
bye.
very much. Once again. Bye, sir. Now I will hand over to Rushit for further instructions. Participants, please stay. And I again thank you from bottom of my heart for such a wonderful interaction. Keep it up. Thank you.
ગિરીશભાઈને તો ફોન કરવાનો બાકી છે.
Good. Rushit?
Thank you, ma'am.
એ લોકો તો કશું કરતા નથી.
Now,
કીધું ને તો
yes.
તરત ના કે તો સર એલ્યુમિનિયમ છે એ બધું કરશે.
Now every participant,
એટલે
please take a
ડેટા
note.
કલેક્ટ કરવા માટે થઈને એક ગૂગલ
We will have a break till 1:30 p.m. The next session will be conducted by Dr. Kamlesh Upadhyay sir on pandemic management at 1:30. It will be going such an informative session, so all can leave this meeting and join sharp at 1:30 p.m. Thank you.